a hollow cylinder and a solid cylinder have the same outer radius of r equals 0.6 meters and mass of 4 kilograms, and roll without slipping on a surface towards a ramp. Bump, bump, bump. All right, make sure this looks reasonable. So this is the solid, that's the hole. Looks like the ramp starts, not important. So, without slipping, so there is friction on this surface. Okay, if the two cylinders initially have the same speed, I'm going to assume translational speed, with respect to the flat surface, and continue to roll without slipping up the ramp, which one goes up further? Okay, so the thought process here should be, you see, goes up further. And it's like, okay, so that means energy potential, MGH. So we want to find out which one achieves the highest H. So we're just going to do an energy balance here. We're going to do it right here. So we'll do energy kinetic initial. This will be the cylinder. Erase this part over here. So for the cylinder, we have energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final. I'm going to do the same thing for, nope, I'll do the solid. What is that, a cylinder? Yep. I'll call that one the cylinder. I'll call this one the hoop, because it's like a hollow hoop, maybe. And we'll do energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final. So taking a look at these, we talked about which one goes up further. So ideal, it's going to reach its maximum height when it stops. So go up the ramp and then stop. So at that point, if it stops, its energy kinetic final will be 0. So these will go away. We'll assume that the ground is 0. That's just for convenience. And so we're left with mass times gravity times height here, which we know they have the same mass. We're going to assume gravity is the same in both scenarios. And so the only difference here then would be height. So these will both be MGH. And potentially different H's. Probably different H's. But then this energy kinetic here, we're going to have two parts to this energy kinetic. Normally you just have your 1/2 mv squared. But this time we're going to add 1/2 I omega squared. So this part is going to be the rotational kinetic energy. So this I right there, that's the moment of inertia. And this is angular velocity. I'm going to say velocity. I guess it's probably speed because I don't have a little vector thing over it. But angular speed. Rotational speed, angular speed. And so this is the equation we're going to use for kinetic energy. Your thought process might, you might be kind of rebelling in your head because you're like, well, energy kinetic is just motion. And it's like, well, yes, that's true. But if you break this down into components and this is rotating, you'd be like, well, that small part is moving that way. That small part is moving that way. And you can break these all down into individual components. And like, there's a lot of energy there that really isn't captured by just the velocity, the translational speed of the object. So really, these two are the same equation here. It's just that this is representing the little interior parts which are not contributing to the translational, not creating they all kind of cancel each other out. Do they all cancel each other out? I don't think so. Interesting. Rotating, not rotating. But there's no deep philosophical difference between the two. They're both talking about the same phenomenon. Okay. Another important thing to notice is there's a relationship between angular velocity and linear translational velocity. And when it says, you specifically see the phrase without slipping, that means you can draw a relation between them two. We know the relationship. And the relationship is, I start with x equals r theta, v equals r omega, and a equals r alpha. Where this is the angular version of the, kinematic equation component. So we have distance, speed, and acceleration. We have angular distance, angular speed, angular acceleration. And the reason I start with the this one and then write these down because they're all similar. This is just a mnemonic that I use. I can check this one because if you think of a circle, it's like, okay, circumference of a circle, 2 pi r. So if you think about going around in a circle, well, the radius, that's going to be r. And then if you go around the circle, it's going to be 2 pi. So it's like, 2 pi r. So if you go completely around a circle, you'll cover a distance of 2 pi r, circumference. But then also by the angular, it shows you'll also cover 2 pi r. And so that way you can kind of see, okay, intuitively, those are equivalent, the same thing. And once you have one, then you can just do the same pattern for all three of them. That's why I usually like to start with x equals r theta. That way I don't accidentally write like xr equals theta or get them backwards or inverted. Nope. And this is just something that's worth memorizing. Okay, so we got that concept down. The big thing with rotational is you want to really make sure you set everything up correctly because it's so easy to get way off on a tangent and then just fall off the edge. You don't want to do that. You can run around in circles with this stuff. No puns. Nope. You can keep going around and around with these things and spend a lot of time and get absolutely nowhere. So it's really good to have a good conceptual understanding about what your equations are doing. Okay, so we've kind of got this idea here that we have 1/2 mv squared, 1/2 I omega squared on both sides, and they're going to equal mgh. So I'm going to come back up here, rewrite things. This is going to be the cylinder, and we have 1/2 mv squared plus 1/2. This is the moment of inertia. It's similar. It's the angular equivalent to mass. Well, you should have learned about that already by now. If not, we'll kind of go over the details as we go. And then if you notice, this is basically the same equation between the two, but instead of mass, we have I. Instead of velocity, we have angular velocity. And you'll see that there's an analogy between all the two. So if you're a crazy good expert on kinematic equations and just linear motion, then angular is much, much easier. If you're kind of flaky on linear, then angular is going to throw you for a loop. So mgh, okay? This is for the cylinder, and I'm going to do the shell one right over here. So, nope, loop. I'll go call it the hoop. The hoop. 1/2 mv squared plus 1/2 I omega squared equals mgh. Okay, sounds good. So what we know so far here is these are both the same mass, and they both have the same translational translational speed. And so this 1/2 mv squared here is actually going to be the same as this 1/2 mv squared there, because they both have the same mass and they both have the same translational speed. So I'm just going to rewrite this, and I'm going to call this E. It's just an amount of energy. It'll make it easier to cancel out later. So I'm just going to be like, all right, don't have to worry too much about that. But now, the part that's going to be different is this part right there, I. So if we look at that, so we're going to find out what the moment of inertia is. This is based solely on the geometry of the object. So if we go over to Wikipedia, we have a list of moment of inertia. These things can be derived. Well, they were derived. We could figure out how to derive them. Not worth our time. So there's basically a list. You, for the most part, don't have to memorize them, but there's a few you should know. So one of them you should know is the moment of inertia of a point charge. I equals mr squared. So if you just have a point and it's going around in orbit, moment of inertia of that is going to be mr squared. If you have a, I wouldn't memorize this, but you'll come across rods a lot. Disk is 1/2 mr squared. And then a cylindrical shell, the hoop that we have, it's going to be about mr squared. And it has to be infinitely thin, I think. Negligible thickness. So 1 mr squared. So we have mr squared here, and then we have a solid disk, which will be 1/2 mr squared. And this is about the z-axis right there. So these are 1/2 and 1. Hop, come back. So now, when we plug this in, this is the cylinder. So we're going to have, get a more exciting color, light blue. So this will be 1/2. I'm going to leave off the E because it's inconsequential for this. This will be 1/2 m, I'm going to use big R, squared, times, and now I'm also going to convert this omega into velocity. So just because I feel more comfortable with velocity, so if we look back at what we talked about over here, we have V equals RW, or omega. Omega then equals velocity over R. Come back over here. We then have V squared over R squared will equal mgh. And I just dropped off that E. We can drop it off both sides. Since it's the same off both, I know this is not a formal proof. Since they're the same on both, and we're just looking to see which one's bigger, we can just drop it off and it won't change the outcome. Okay, here's the loop, 1/2. Now this is just going to be m big R squared without the 1/2 times V squared over R squared equals mgh. Do some canceling. So with the R's squares, those cancel. The masses, those cancel. And we're going to leave the g's there. So solving this right side over here, we have V squared over 4g equals h. Solving this side over here, and I understand I kind of canceled some things out that I really shouldn't have, but this still since I'm comparing these two, this is all that's really important. So this side over here, we have V squared over 2g equals, I make them squiggly, so kind of sort of approximately, equals h. So this side over here with the cylindrical will only go up something over 4, and this side on the hoop will go up something, V squared over g, kind of sort of, over 2. So since this side is bigger, twice as big, the hoop will go higher. So hoop, higher. Now let's take a look at that and see if we can logically make sense of why that would be. So if two cylinders, initially the hoop and the solid cylinder, have the same speed with respect to the flat surface and continue to roll without slipping, which one will go up further? So we said the cylinder, the hollow cylinder, the hoop will go higher. So we said this one will go higher. And it said twice, but that we basically neglected the kinetic energy. So based on just if the kinetic energy brings it up to there, then maybe twice as far based off that, it would then go based off the rotational energy. And this makes sense. So it is harder. So when you have, it's harder to spin something that's big than something that's small. So if you have something that's really tiny and compact like this, it's easy to spin a dot. But if you have something much bigger like this, all this mass on the outside, that's going to make it harder to spin. And since it's already given to us that they're going the same speed, same translational speed, and since there's no slipping, means they have the same rotational speed as well. And this hoop, since all the mass is on the outside, is harder to spin. But since it's already spinning, it now has that more energy stored up. And it's going to take that stored rotational energy, and kind of stored, and when it expends that kinetic energy and turns it into potential energy by rolling up the ramp, it's going to have more energy to expand, even though it starts with the same velocity based on the geometric orientation, i.e. all the mass being at the outside. That exterior outside mass is going to contribute more to the total energy of the system than the solid cylinder, which has some mass at the outside, but also has some mass at the inside, kind of a gradient. And so that's why we have more energy in the hollow loop than we do in the solid cylinder. And we kind of showed the basic idea of that mathematically, and intuitively, this makes sense. At first I was like, wow, you spent like 15 minutes on this problem, and I'm only going to have like 2 minutes, maybe 1 minute to solve this. How am I going to, go through all this, on a test timed evolution and get the correct answer? The answer is you don't. You look at this and you intuitively think about it. This math is just to kind of reinforce your concepts. But if you see this on an exam, you're like, okay, which one's going to go further up? There's going to be, if they're going the same speed, more energy with the hoop than with this, which makes sense. So you then have to take that and be like, all right, that's going to have more energy to create more potential energy, which is going to go higher. You need to be able to do this understand pretty quickly, which is why the base conceptual knowledge of angular motion is so important. Okay, focus, next problem. So we already did that. So I'm going to erase this because it's big and clutterful. Whoop. Click. All right, now we've got a cleaner real estate. Get rid of this 1/2. If the two cylinders initially have the same speed and roll without slipping with respect to the flat surface, but there is no friction on the ramp, then which cylinder goes further up? Okay, excellent. So I'm going to go back to the same concept we had earlier. So we had energy kinetic equal, or initial, plus energy potential initial equals energy kinetic final, plus energy potential final. So this is what we're looking for. The energy kinetic final is 0, energy potential initial is 0. We break this up into two portions. We have 1/2 mv squared plus 1/2 moment of inertia angular velocity squared equals mass times gravity times height. And what this is saying is the two cylinders initially have the same speed and roll without slipping with respect to the flat surface. So we have something rolling here, and there's a relationship without slipping, which means that you have this V equals R omega relationship between the translational and angular speed. And so there's this, I guess, proper division between the kinetic, or the translational and rotational energy. Flat surface, but there is no friction on the ramp. So if there's no friction on the ramp, what's going to happen is this ball is spinning, but then when it gets to the ramp, it just keeps spinning. It's going to go up a while, and it's still going to be spinning, and then it's going to fall back down the ramp while still spinning. What that means is this hoop and this cylinder are going to be unable to convert their rotational kinetic energy into potential energy on the ramp because they don't have the grip on the surface. So if you think of it from a more, I guess, technical point of view, more formal point of way, the way this works is you have the cylinder rolling on a flat surface, and you have friction going this direction, but then you have the rotation going this way, so the ball is basically falling forward. And that's how you get this relationship of V equals RW without slipping. Well, if you have a ramp with friction, this is with friction now, what's going to happen is as it goes up, the potential energy potential goes up because it's building up potential energy, but it's doing that at the expense of kinetic energy. We'll say energy kinetic, in this case 1/2 mv squared. So it's slowing down. But since there's a relationship between the angular velocity and the translational, you basically have something along the lines of a torque being created because the velocity it has an accelerating going down the ramp because it's losing its translational speed going up, and you have a torque due to friction that's basically slowing down this angular velocity. And that's kind of the mechanism that it uses to basically climb the hill by rolling up it. Well, when we get rid of friction, they can't do that anymore. And so what happens is it still has this potential energy on the other side as well. So what happens here then is this idea here of energy kinetic going to 0 at the end when it's climbing up the hill, I've said to 0, I should not have, because there's still that I omega squared going to be left. So really what's going to happen is we're going to have plus I omega squared. So we start with our translational kinetic energy, we end with potential energy, and this rotational energy is never converted into height on the ramp because we need that friction to do that. And without that friction, we keep this rotational energy. And that rotational energy is what differentiated the solid cylinder from the hollow cylinder. So long story short, which cylinder goes up further? They both go the same distance. Because the only thing that differentiated them was the angular energy due to rotational energy. And the only way that rotational energy can be converted into potential energy is through the friction on the ramp. And without that friction, that's not converted, and the two shapes will maintain their rotational energy until they get back down to the base here, which will then continue to roll. So I hope that made sense. I'll go over the next two problems next time. This is so in depth, and there's so much backstory to explain with this that doing it all at once would be a little excessive. So appreciate you stopping by. I will see you next time.